Our first standard explains the relationship of the side ratios of a right triangle between hypotenuse, adjacent, and opposite. We can explain these ratios by using sine, cosine, and tangent.
The sine of theta is the opposite over the hypotenuse. The cosine of theta is the adjacent over hypotenuse. Tangent of theta is opposite over adjacent. For future reference, these are the inverse ratios for a right triangle. To remember the ratios of a right triangle, use SOHCAHTOA. The sine of theta uses opposite over hypotenuse. The cosine of theta uses adjacent over hypotenuse. Tangent of theta uses opposite over adjacent. To find the theta of the right triangle, in this case we are given the opposite over hypotenuse. So we would use sine to find x. We know we're using sine. We set the equation up, and it's opposite over hypotenuse. So 12 will go on top, and 13 will go on the bottom. 12 over 13 equals 0.92307. So to find theta, you plug this number in to the inverse of sine. 207. I know what that says. This equals 67.4. So the sine of theta equals 67.4 degrees. Our second standard shows the relationship between sine and cosine, which is often also called the complementary angles.
The second standard that we come across is the relationship between sine and cosine. The relationship between those two is that they are complementary angles, which means they equal 90 degrees when added together. Also, they are frequently called cofunctions to each other. Be able to recognize when people use both words. When you hear sine and cosine are complements or cofunctions to each other, that means that when sine and cosine are added together, they equal 90 degrees. When using sine and cosine, you will be given a problem that looks something like this. But in order to do sine and cosine, you must first label the sides of the right triangle. To find the opposite side, we start with our given angle, which is 53. Then we go straight across, and the side that we bump into here is the opposite side. Now, to find the hypotenuse, we start at the 90-degree angle in the right triangle. We go straight across, and the side that we bump into here is the hypotenuse. Now we must find the last side, which is the adjacent side. We can find this by process of elimination by seeing that we already have the hypotenuse and the opposite side labeled, so that leaves this to be the adjacent side. Also, we can find it by seeing it is the only side besides the hypotenuse, which is already labeled, so it's not that, by it connects to the angle that we have. Now that the sides of the triangle are labeled, we can now use sine and cosine, and the easiest way to remember their formulas is by using SOHCAHTOA. For this standard, we're just focusing on sine and cosine, so for now we can forget about tangent. Now we can set up sine. We use sine in the angle of 53, since that's the angle we're given, and we use opposite, which is x in this case, over hypotenuse, which is 10, and we know this by using SOHCAHTOA at the top right-hand corner. Before we set up the formula for cosine, we first have to find the angle measurement for cosine by using this formula. We find this first 90 degrees because we know that the angle of sine and cosine has to equal 90 degrees as well to equal the whole total amount of a triangle, which is 180. So we take 90 minus 53 because 53 is the angle measurement of sine, and we get 37. So 37 degrees is your angle measurement for cosine. Once we found the angle measurement for cosine, which is 37, we can now set up the formula for cosine. Cosine of 37 equals adjacent, which is x, over hypotenuse, which is 10. To clear confusion, sine's work will be written in blue, and cosine's work will be written in pink. Before we begin, there's a rule that can help you remember what to do when you come across an x in the formula for sine and cosine. If you see that x is up high, as in this problem here, you multiply, and if x is down low, you would divide. For the work of sine, x is up high, so you multiply the sine of 53 times 10 equals x. In this case, when you do this in your calculator, you will get 7.98 something something something, and it will go on for a while. Always look at the directions, but in this case, I want you to round to the nearest whole number. So when you round to the nearest whole number, it would be 8. For the work of cosine, x is also up high. So we multiply the cosine of 37 times 10 equals x. You will again get 7.98 something something, and again, I want you to round to the nearest whole number. So this answer will be 8 as well. Now that we've solved for x and we figured out x equals 8, we can plug it back into the triangle on the opposite side. Now we have every angle measurement for our triangle, and our triangle is complete. Before we begin our last standard, I want to give you a little bit of background information about it. In ancient Greece, there was a mathematician named Pythagoras. He discovered how to find the sides of a right triangle by using a squared here plus b squared here equals c squared, which is the hypotenuse. Once he came up with this theorem, he wanted to name it after himself, thus the name Pythagorean theorem. And there's a catch. You can only use the Pythagorean theorem with a right triangle. And we know it's a right triangle because there's a square on the only 90-degree angle in the whole triangle. The Pythagorean theorem states that in a right triangle, the square of the two bases equals the square of the hypotenuse. When using the Pythagorean theorem to find a missing side measurement, you first have to figure out whether you're trying to find side A, B, or C. If you're trying to find side A or B, you need to subtract the square of either A or the square of B from the square of C to get your other side measurement. If you're trying to find side C, which is the hypotenuse, you need to add the square of A and B to equal the square of C. Before we begin, we must know which sides are which. The two bases are sides A and B, and the hypotenuse is side C. Now that we know the sides of the triangle, we can plug it in the formula. This is side A, so we plug in 3 for A, and we still keep the square. Since we don't have side B, we can keep it B for the variable and still keep the square. And side C equals 5, so we plug in 5 for C and keep the square. The easiest way to do it now is to square your numbers. Now to get b squared by itself, we must subtract 9 from both sides. So we get b squared equals 16. Now to get the value of b, we have to take the square root of both sides. So the square root of b squared is b, and the square root of 16 is 4. Now that we have solved for variable b, we can plug it back in to the triangle. Now we have every part of our triangle, which creates a complete Pythagorean triple. This example is not in your notes, so if you are confused on this, I would copy this down and fill it in as we go along. When we're using the Pythagorean theorem to find the side lengths, in this case we have side A and side B. We do not have the measure of side C. So we plug this into the formula, side A being 3, always remember to square both of your sides, and side B being 4. We do not have the hypotenuse, so we'll put C as a placeholder variable and remember to keep it squared. The next step would be to go ahead and square both A and B. 3 squared is 9, and 4 squared is 16, equals C squared. We can go ahead and add these two together, and you'll get 25, equals C squared. This is not our answer yet because this C is still squared, and we want it to just be the variable C. So in order to do that, we have to square root both sides. C squared is just C. 25 squared is 5. So 5 equals C is your answer. And you would plug this back in here, and you would get the triple 4, 3, and 5.